Rajat Manga is a director of engineering at Google, where he works on TensorFlow. TensorFlow is a framework for numerical computation developed at Google. The majority of TensorFlow users are building machine learning applications, such as image recognition, recommendation systems, and natural language processing. But TensorFlow is actually applicable to a broader range of scientific computation than just machine learning. TensorFlow has APIs for decision trees, support vector machines, and linear algebra libraries. The current focus of the TensorFlow team is usability. There are thousands of engineers building data-intensive applications with TensorFlow, but Rajat and the rest of the TensorFlow team would like to see millions more. In today's show, Rajat and I discussed how TensorFlow is becoming more usable and more accessible. And we also discussed some of the developments in TensorFlow around edge computing, TensorFlow Hub, which allows people to share modules of their TensorFlow applications. And we also talked about TensorFlow JS, which allows TensorFlow to run in the browser. We'll have an upcoming show about TensorFlow JS where we'll do a deeper dive in the near future. If you want to hear the previous episode that we recorded with Rajat, as well as some other episodes about TensorFlow, Keras, and other related topics to machine learning, we have all of our episodes in the Software Engineering Daily apps for iOS or Android. We've got tons of episodes on blockchains, distributed systems, business, lots of other topics. You can also find all those episodes at softwaredaily.com. And if you want to become a paid subscriber to Software Engineering Daily, you can hear all of our content without advertisements, and you can subscribe at softwaredaily.com. Also, all of the code for our apps and our website, it's all open source. If you're looking for an open source community to be a part of, you can come check it out at github.com/softwareengineeringdaily. We'd love to have you as part of our community. So thanks for listening, and let's get on with this episode. This episode of Software Engineering Daily is sponsored by Datadog. With automated monitoring, distributed tracing, and logging, Datadog provides deep end-to-end visibility into the health and performance of modern applications. Build rich dashboards, set alerts to identify anomalies, and collaborate with your team to troubleshoot and fix issues fast. Try it yourself by starting a free 14-day trial today. Listeners of this podcast will also receive a free Datadog t-shirt at softwareengineeringdaily.com/Datadog. That's softwareengineeringdaily.com/Datadog. Rajat Manga, you are the Director of Engineering at TensorFlow. Welcome back to Software Engineering Daily.
Thanks, Jeff.
The last time you came on the show, we talked about some of the basics of TensorFlow and your work on the framework. Today, I'd like to talk more about the progress of machine learning and how you are seeing that through the lens of your role on the TensorFlow team at Google. Let's just talk about machine learning developments to start with. What are the machine learning developments in the last year that have surprised you?
I don't know if they're surprising. They're all making great progress in the direction we started in. The pace of progress is pretty fast, of course. A number of exciting areas have been some of the progress in robotics, where you can now learn from other humans. You can learn from simulations rather than needing lots and lots of data. So, progress in areas where you can learn with less data has been very, very interesting. The progress on the generative models with, especially the generative adversarial networks and the variations of that has been really great. And we're seeing some, amazing things that they've been able to create as well. And then, we're starting to see very exciting, again, from a research perspective, exciting ways where people are trying to mix this with other things that people do. So, for example, in the music domain, the Magenta project has made a lot of progress in combining some of these creative techniques from machine learning with artists and see how the two can work together and come up with very interesting pieces of music.
So you gave a number of interesting developments. Magenta is particularly appealing to me as a musician. I've talked to the Magenta team, and I find that project particularly appealing because I see it as that's a place where it leverages the human-computer interaction side of things. They seem to really be exploring how can a machine learn quickly from a human and learn to collaborate with the human more effectively. But on the TensorFlow side, which is where you're focused, the objective of the TensorFlow team over the last year has been to make the framework more usable. Why has the goal of usability been at top of mind for the last year?
I think where we started out was enabling new kinds of research, and that continues to be important. We definitely want to make sure machine learning continues to progress. But then beyond that, one of our big goals has been really to bring all these exciting developments, exciting advancements to many more people across the world. And to do that, we really need to make software, we need to make tools that are really, really easy to use, right? So with TensorFlow, the goals have been, you don't necessarily need, to understand all the math. You don't necessarily need to understand even backpropagation because, a lot of that is taken care for you. And then just in terms of the library, the API, going from the lowest level where you have full control, we're trying to go higher and higher where you get to do things. And then slowly you can, as you learn more, you can do more interesting things or more different things. But just to get started, it should be very, very easy.
What are some of the more specific usability efforts that you focused on?
So I think a couple I'm really excited about. So one is what we call eager execution. And what that does is, what TensorFlow used, what it started with was this idea of you build a graph and then you execute it, and the graph represented the machine learning model. And the reason we did that was that really allows us to optimize it using a lot of the compiler techniques and really scale it out across large scale, distributed systems and so on. Now that's great. But what that does is when a developer starts out, they have to think about that graph and think about it that way. With this new idea of eager execution, the idea is you don't have to build a graph. You're just programming. If you're familiar with Python, you're just writing Python code, and that internally just executes TensorFlow code and is optimized for CPUs, GPUs, TPUs, whatever. And then, so it takes away one of the things that you had to think about earlier and just makes it a lot easier and more natural in Python itself. Now, going from there to scaling, you still have all the good stuff that you used to have with TensorFlow. So you can still use pretty much the same code and create a graph from that instead, or scale it out to a really large cluster if that's what makes sense. But it really allows you to cut that friction down when starting out. So that's one. Another interesting piece has been just the higher level APIs that, we started to invest in building these ideas of layers and models and so on. What we realized, and, we have Francois Chollet here as well, who's the author of Keras, and that was an exciting way for our developers to access these models, to access deep learning as they're getting started. So we've really worked to integrate that right into TensorFlow and make it really easy to get started with that as well. So I think for typical Python developers, those are two big things. I would say there's a different class of developers almost, and some people who like different languages, JavaScript being one, especially on the web, and that's another area that I'm happy to talk about. There's tons that's happened there as well. We've brought TensorFlow to the web browser as well.
Yeah, we could just jump into TensorFlow JS. So that was a recent announcement, and this allows for training and deployment of machine learning models in JavaScript. What are the domains in which people want to use JavaScript for machine learning?
I think we are just starting out. So there are a number of things that we can think of, right? So often we push, we've seen over time that people want to do machine learning outside the data center as well. Over the last couple of years, we've seen people push these things on phones and so on. Over the last year, some folks, some developers on our team said, okay, what if we could do more in the browser, right? What if we could accelerate it? There were some libraries before that would do the basic math, but what these guys did was not just take those ideas that that we did in the data center, but also accelerate them in the browser using the GPU, whatever you have on your machine. So it can go pretty fast. Now with that, what we've seen is areas where, the first one that comes to mind is you want to get started, you want to teach people something, you have demos to show. You can include ML in all of those. So we have some very exciting things that people have built. People have built games in the browser with, using different kind of gestures, etc. And also, once it's on in the browser, it has access to your camera if you wanted to. It has access to your audio stream if you wanted to. And you can do pretty interesting things in combining all those together.
Is that important because you can have learning take place on the client-side device and not necessarily have to shuttle the data back to the server?
So that's definitely part of it, I think. The other part I would say is the fact that you don't have to install anything. You just go to this website and it works, right? It's a no install completely. You go someplace and it's just working. And I think all of that, again, reduces the friction for a developer, and then beyond that, their users as well to get started, which is a huge value, I think.
And when you say TensorFlow runs in the browser, does that, or TensorFlow.js, it runs in the browser, does that mean that these, what had to be built in order to implement that? Because I know TensorFlow runs in many different languages, but I'm wondering what that actually means. Does that mean that you can write the code for models in many different languages, or that you have defined interfaces for compiled models to interface with those languages? What exactly do you have to define to say that you've ported TensorFlow to a different language?
Right. So I think there are a number of things that happen with different languages, and browser is somewhat special in some ways. So often what we do for different languages, and people have used Scala, Java, even Julia, and many other languages really to do that. What we often do is TensorFlow has an API that offers access to all the operations that it provides. It offers access to just execution of these operations or building graphs and all of that stuff. Now, often for these languages, what that means is they create wrappers around these functions and these operations and make them available in that language. So people can then build on top of that. People can, again, build their own models there, or, more often just models that have been trained, say, using Python, just the more common one today, and then take those models and really execute them from a different language. Now, all of this typically uses the same TensorFlow runtime in the backend that we have, which can scale and do all of that stuff. In the browser, the interesting thing is you don't have access to all this other backend because that's in C++. The browser doesn't allow you to run it for good reasons, for security. And so in the case of the browser, we actually took the same APIs that the TensorFlow has in many other languages, and really wrote a custom backend or a custom optimized operations for these that can run in the browser and that are potentially accelerated using techniques like WebGL, which give JavaScript code in the browser. The advantage. So on the JavaScript side in the browser, you can build your models with JavaScript, or again, you can take models that were trained in TensorFlow otherwise, convert them using a tool, and then run them in the browser using all these APIs.
So when I build and train a model in Python using TensorFlow, the end result is a model that runs. It requires C++ to run. Is that what you said?
Right. So behind the scenes, when you write your code in Python, behind the scenes, most of TensorFlow code is written in C++. It's all compiled, and so you don't care. But that is a library or a binary that's running there. And that isn't something that can be shipped to the browser. But for most other languages, that's what gets used because it really allows us to optimize that down to whatever we need to.
So you had to write some kind of interpreter to translate that C++ code, the model that would run in C++, to some minified JavaScript version that could run in the browser?
So it's actually a number of things there. So one, in the browser, we defined a nice interface that the developers could code against. And then from taking the model and deploying it, The model itself is not in C++. The execution engine is in C++. So one way I like to explain that is, you could think of the model as your Java bytecode. So you write a Java program. In this case, we write it often in Python, but it could be in Java too. And then when you sort of train the model or you execute it, eventually we get this graph, which is sort of our bytecode or an intermediate representation. And that's represented in protobuffers typically, along with some information and the weights and the data, etc. So it's this intermediate representation that's really converted into an optimal format for the browser, and then the code in the browser actually interprets that.
Oh, right. Okay, so it's in a protocol buffer after you train the model, and so in the browser you need to define a way to interface with that protobuf. Is that what you said?
That's correct. And to think of that protobuffer as really defining a simple program that represents your model, and the browser has code that interprets that basically and executes that model.
And this reminds me of, I think when I was reading about some of the other announcements, the recent TensorFlow announcements, there was the TensorFlow Lite, which is another model for running TensorFlow in less resource constrained environments. And I think in those environments, you actually want to define not a protocol buffer, but was it a flat buffer? Is that right?
That's right. So that's another format that's used that's optimized for those environments. That's, uses less memory. It's easier to get started. It's faster to get started and so on.
The octopus, a sea creature known for its intelligence and flexibility. Octopus Deploy, a friendly deployment automation tool for deploying applications like .NET apps, Java apps, and more. Ask any developer, and they'll tell you that it's never fun pushing code at 5 p.m. on a Friday and then crossing your fingers, hoping for the best. We've all been there. We've all done that. And that's where Octopus Deploy comes into the picture. Octopus Deploy is a friendly deployment automation tool, taking over where your build or CI server ends. Use Octopus to promote releases on-prem or to the cloud. Octopus integrates with your existing build pipeline, TFS and VSTS, Bamboo, TeamCity, and Jenkins. It integrates with AWS, Azure, and on-prem environments. You can reliably and repeatedly deploy your .NET and Java apps and more. If you can package it, Octopus can deploy it. It's quick and easy to install, and you can just go to octopus.com to trial Octopus free for 45 days. That's octopus.com, octopus.com. What are the trade-offs you make if you train a model and you throw it into a protobuf versus a flat buffer? What are the trade-offs you're making?
So from the model developer's perspective, it really doesn't matter. They both represent the exact same thing. You can have the same kind of model running in the browser or on the device. The difference is more from, these are formats that were built for different reasons. And the reason the protocol buffers are interesting and why we started from them are they offer a lot of flexibility. We use protocol buffers for lots of different things and storing things where they might change over time. So versioning, etc. They're really, really good at that. Flat buffers still offer some of those advantages. They still have some of that flexibility, but they trade off some of the other flexibility for making it really lightweight, because if you want to deploy it to, say, a small phone or even a tiny device, you really want to optimize for that last bit of space. When you get started, say, when you load the model the first time, the way flat buffers encode it, it's just much faster to get started, so the overheads are lower there. So you're trading off a bit of flexibility for a bit more performance there.
I see. So it's not about execution as much as perhaps the format itself. So protocol buffers are used for microservices and all kinds of other things throughout Google, and they're widely used outside of Google as well. But you may not use flat buffers for defining interfaces for your microservices. You want to use flat buffers more specifically for these kinds of domains, like resource-constrained machine learning execution environments.
Exactly. In fact, I believe they were built initially for game developers, for gaming kind of environments.
Speaking of devices and IoT machine learning deployments, are there devices on the market that maybe they're just types of devices where we would love to deploy machine learning models to them, but because of legacy technology, I'm thinking of industrial environments, maybe oil rigs or agricultural situations. Are there computers running in these environments where we can't yet deploy machine learning models to them just because of the way that the compute infrastructure was built?
I would say not really. Today, where we are, I think we can deploy machine learning to pretty much every place you have a computer. Now, of course, depending on your environment, how you take advantage of it and how it's connected to what you have there is different. If you are in a legacy environment, if you don't have access to all the sensors that you're collecting data from on that computer, you're not going to gain much value out of it. But that said, if you have a computer and you don't need a lot of computing power for some of these deployments, you can really deploy things now. And in fact, that's one goal that we have. We want to make sure that, and TensorFlow Lite was this was a big reason to build TensorFlow Lite, that we want to make sure anytime, any place, remote, wherever you are, if you have a computing device, you should be able to run machine learning on it, because if not now, you will want to do that in the future.
Are there other trade-offs that the developer needs to keep in mind when optimizing for resource-constrained environments, whether we're talking about mobile devices or sensors in an agricultural field?
Definitely. So from these devices perspective, if we're used to our workstations or laptops or even tablets, those have a lot of memory, space, and the kinds of things that they can do. As you start to go down to these smaller sizes and form factors, it's as if you are like 20 years ago where desktops were, and you're constrained. The amount of memory you have is much less. The amount of storage space you have is much less. So you have to be careful about what you do with it. Say on a workstation, you would be fine starting with, say, just writing a simple loop that just works. And maybe on your workstation, that takes a second or even less to execute. Now you run the same thing on this tiny device, and it might take 10 times that because of the compute power, because of the RAM capacity, and so on. So you have to think about that as you write the code for these kind of environments.
TensorFlow started with an emphasis on deep learning and neural nets, and now there's a wider array of libraries available. So within TensorFlow, you can interface with decision trees and support vector machines and linear algebra libraries. And when I think about those features, it starts to look more like a flexible mathematical tool that's not necessarily constrained to machine learning operations. Do you see TensorFlow being a tool that could have the functionality of other scientific computing tools? Like I'm thinking MATLAB, for example?
Absolutely. I think at its core, when we designed TensorFlow, we wanted to layer things in. So the core itself is really a numerical computation library, exactly as you said. And you can build lots of different things on top. Of course, the first thing we started with was deep learning and neural networks. But as you've seen, a lot of these different things have been built, some by us, some by other teams at Google, and many by folks outside Google as well, because they see this core computing library that offers a number of things. It offers support for distributing across many nodes. So like in the scientific use cases, you want to use a supercomputer, you can do that with TensorFlow. If you want to accelerate your code on accelerators like GPUs or TPUs, you can do that with TensorFlow. You're not limited to CPUs itself. So it offers a lot of the advantages the good things that you want from a math library, from a numerical computation library. And then on top, we've layered really nice APIs and so on that you can directly interact with or build other kinds of things on top. And that's what you see with all these different libraries and probability or linear algebra and so on.
It really expands what I think about TensorFlow, the potential of it, because initially I saw TensorFlow and think, oh, this is a machine learning library that's like Torch or something like that. But thinking more about the name TensorFlow, all it really means is a multidimensional matrix of numbers that is positioned through a data flow graph. And if you just think about numbers flowing through a data flow graph, well, what that symbolizes from a computer scientist's, from a programmer's perspective, is a much broader array of tools. And I haven't thought deeply about where that could potentially go. Do you have an idea for any kinds of applications that somebody could build with this kind of framework that, maybe we can't even, somebody wouldn't really be able to build today, or people are not building with TensorFlow? What's your grandest ambition for the kinds of applications that people might be building with TensorFlow in the future?
Some of the areas that we are already starting to see some interest is, you talked about scientific applications at large scales. A lot of these run on really large scale supercomputers. Now we are seeing, some of those are simulations. So let's say weather patterns, you're simulating what it might be in a day or two. Now, often what people want to do, and it's interesting, where they want to mix some of these simulations with the machine learning side. So they want to apply deep learning models to do some of these predictions as well. And where we started seeing people doing is already applying deep learning and scaling it and running TensorFlow on these huge supercomputers to do these machine learning things. I think what we'll see more of is combining that with the simulations as well. And so you have one environment, one computing platform where you can do all these kinds of things. So I think at the large scale, I think that's really, really exciting to me. On the other side, and if you were just talking about devices, there's a lot you want to do on the really remote at the edge, because more and more, you talked about these industrial places where you have these tiny devices and so on. I think all of them are collecting data. All of them have sensors today. And the reason to have them is you can make smart decisions about what's happening. Now, it's not really feasible to ship all that data back to some cloud and process it. And often it'll be very valuable to run these things on those devices. And, prediction is one part of it. But now that you have a platform that allows you to do a bunch of things, maybe use the existing algorithms we have, maybe you build your own things custom for what you have and really do all of those in one single platform. I think that's going to be really exciting.
And not just the model of doing computation at the edge, but there's also the middleware device potential, where if you have cars driving around that have computers in them, or you have drones flying around that have computers in them, or you have people's smartphones where maybe they have spare compute cycles, and if you had people walking around with their smartphones that had spare compute cycles, and you've got, I don't know, a machine learning street light that is needing to do some kind of computation, it can maybe offload some of that computation onto nearby cell phones. Like the model for TensorFlow of being able to distribute computation among different nodes seems like it's well positioned to have that kind of computation distribution potential.
That's right. Those are some really interesting ideas. And yes, having a platform that lets you do things like that and combining this computation and distribution potential to access different kind of computation will definitely enable new interesting ideas and combinations of those.
Yeah. It's one of those things where you can see that future evolving, and I can just imagine it must be very hard to design, because you don't want to prematurely optimize for that kind of future, but at the same time, you do want to leave design space open for that kind of future. Is that something you even think about, or do you think it's something where you've designed software for long enough that it becomes intuitive, the kinds of abstractions that you want to build, where you don't paint yourself into a corner and are unable to take advantage of that kind of future?
Yeah, I think it's a bit of both. So yes, the experience that me or many folks on the team have had designing systems like this definitely helps. We have a lot of really smart engineers who've built amazing systems here before. That definitely helps in designing basic APIs that are more likely to succeed. That said, we don't always get things right. And, one of the important things that is, in the world of today with changing needs and so on, and especially with something like TensorFlow, is to keep an eye out for what do people want to do with this and learn from that, right? So you don't want to just get stuck that, okay, this is our design, this is where we were, and we're not going to change it. And a good example that I see there is how we switched from just starting with pure graphs to now executing code directly as well. And I think adding that new thing was hard. We had to rethink certain things, but now that we've done it, and over the last year, I think it's really improved the platform a lot, and it's more accessible to many more users. So you don't want to get stuck with, okay, here's just what it is. Yes, you may have really great designs, and often we do, but not always. We're still learning, and I think we'll continue to improve.
Another recent development was TensorFlow Hub, and this allows for reusable parts of machine learning models. This sounds very appealing. What is an example of a reusable module?
So I can think of a couple of examples. So on the text side, often you have this idea of embeddings, which are basically representations, vector representations of things like words or sentences. And these are interesting because you might train these once on, say, some text data that you have, and often you don't have to have labeled data. This is just regular text that you can train on. And what they might do often for word embeddings is, the way these embeddings work is those embeddings are really, think of those as points that represent those words in a really high dimensional space, where words that mean similar things are closer to one another and words that mean different things are further away. Now, these are very useful for lots of different text kind of models, for natural language processing models. It turns out you can train them once on a reasonably good corpus and use them for lots of different things. So that's one thing that's, I think, very, very useful, and that's something we offer there. Another one that we've seen is often, if you're doing, say, some kind of image classification or something on a very custom task, right? You have your own data set. You might have a really small data set, say 100 or 200 images across a few different classes. Now, clearly, you can't train a really large model just on that small data set. However, it turns out that we and many others have trained these really good models on super large data sets, like the ImageNet database, which is about 1 million images that's available externally. So we've trained models on that data set, and it takes a lot of computing power, like the example that I was talking about recently on TensorFlow Hub. Our best-in-class model took about, I think, something like 60,000 GPU hours to get that kind of accuracy. And clearly, not everybody can train that model. But what you can do is take that model and really take the features from that model and use that for your tasks. So we make the core model available so you can use, and that's accessible to you with the weights from TensorFlow Hub. And so while training your custom model on your task, you can just take that and just execute that to get the features, and just, it helps you a lot with your task. You don't really have to go through that huge computational burden. And it's very exciting that you can, get started pretty quickly.
When someone posts a model on TensorFlow Hub, do they also have to post the data set that trained the module that, for example, if I train a Word2Vec model, if somebody else wants to use that Word2Vec model, then they could be concerned about the bias associated with how that model was trained if they don't have access to the data set. Do the users who post modules also have to post the data sets associated with them?
That's not required. Some of these data sets that we use or others use are public data sets that are available, and you might find information about those. However, we don't want to make it a requirement that you need to have a data set. That said, for the specific issue that you mentioned, where you might have biases, etc., we also have a number of tools to help you understand biases, to analyze the models themselves. For example, there was this specific tool called TensorFlow Model Analysis that we just released as part of our overall TensorFlow extended suite of things to provide you the bigger machine learning pipeline itself. There are a number of other tools as well that we have that help you just understand those models for different kinds of biases, and we definitely hope to help continue to work on that as well.
Users have come to expect real time. They crave alerts that their payment is received. They crave little cars zooming around on the map. They crave locking their doors at home when they're not at home. There's no need to reinvent the wheel when it comes to making your app real time. PubNub makes it simple, enabling you to build immersive and interactive experiences on the web, on mobile phones, embedded into hardware, and any other device connected to the internet. With powerful APIs and a robust global infrastructure, you can stream geolocation data, you can send chat messages, you can turn on sprinklers, or you can rock your baby's crib when they start crying. PubNub literally powers IoT cribs. 70 SDKs for web, mobile, IoT, and more means that you can start streaming data in real time without a ton of compatibility headaches. And no need to build your own SDKs from scratch. And lastly, PubNub includes a ton of other real-time features beyond real-time messaging, like presence for online or offline detection, and Access Manager to thwart trolls and hackers. Go to pubnub.com/sedaily to get started. They offer a generous sandbox tier that's free forever until your app takes off, that is. pubnub.com/sedaily, that's pubnub.com/sedaily. Thank you, PubNub, for being a sponsor of Software Engineering Daily. So I want to zoom out to some of the other associated discussions that you mentioned at the beginning of the conversation and some things that were touched on at the TensorFlow Dev Summit. AutoML is a project that Google is working on to allow people to train custom machine learning models without thinking much about how that training is actually proceeding. I don't know how much, do you spend any time on AutoML, or are you mostly focused on TensorFlow?
So my focus is primarily TensorFlow. I know of that work. I mean, a lot of those folks sit here as well. So I know a lot of those researchers. But yeah, my focus is definitely more on TensorFlow.
Okay. Have there been any learnings from the AutoML team that have impacted how you're designing TensorFlow?
A few things I would say. One, this is another area where the way AutoML works is it's trading off more human expertise for computation. So having TensorFlow really be optimized for these kind of things is really, really important. I mentioned 60,000 GPU hours. That was used for training one of the AutoML models. And when you're getting at that scale, if the tool is not optimized, if it doesn't perform, it doesn't take advantage of the machines and the devices as much as it can, then you're really wasting a lot of resources. So that's definitely been one. Another is it's been interesting to see how AutoML can optimize for different kinds of environments. And, one of the things that they were working on was optimizing models for deployment on devices. So even though they're being trained and they're being optimized to get really high accuracy, they're also being optimized for deploying on devices. So they take into account the kind of computation you can do there, or how long it's going to take, and there's a budget maybe that you have and you want to balance for that. So those were really interesting and sort of leveraged all the pieces that we have in TensorFlow as well.
I've heard a lot of emphasis recently on transfer learning. What is transfer learning and why is it so important?
So this is sort of the example that I was talking about for images. Let's say you have an example where you just have a couple of hundred images, say across 4 or 5 classes. Now, if you want to train a really good model for those, it's going to be hard with just these few images. You're not going to get a very accurate model if you start from scratch, if you have no idea. Even if you use the best description of the model that people have, had from research. So what people often do for cases like this was exactly, what you would get from Model Hub, where the TensorFlow Hub, which is where you have the entire model pre-trained on a different data set, and often it's ImageNet, which has 1 million images or more, and then you've trained it on that. Turns out because images often of natural kind of things are similar in nature, most of that model you can really reuse for a different kind of application. So even for, say, you had a data set for identifying 5 kinds of birds, you can reuse most of that model. So you take that as a module, you plug that in, and just train a small classifier on top. This is called transfer learning, basically, where you're taking the ideas and learning from one data set and transferring it to another data set, which may not necessarily be large enough for this.
And is there any necessary work to make transfer learning a first-class citizen in TensorFlow? Do you try to make transfer learning easier to implement?
Yes, so we allow you to easily control what you're training, what you're not, to easily port models or take parts of modules like these modules with the TensorFlow Hub, where you can say, okay, I have already this pre-trained model from this other task. I want to take this, I want to just change the stop here to change the classifier. All that's really easy. We have tutorials to do that as well. We have examples and so on too.
Another development that you mentioned earlier was GANs, the Generative Adversarial Networks. What are the use cases where GANs are useful?
So GANs are interesting for a number of areas. Often the basic idea is there's one network that's trying to create something, that's trying to generate something, and there's another network that's trying to separate that or discriminate that from whether that's real or not, from real data or not, right? And this forces the first one to keep getting better and the second one to keep pushing it harder and harder and so on. And that's what allows it to learn. So that's the very basic idea in there. These can be used for generating different kind of things. Often where we are starting to see them is for generating images, where people are generating. There was this interesting work from folks at NVIDIA, I believe, where they trained it on lots of celebrity pictures and then let this model generate different kinds of pictures. And if you look at those pictures, they look very real. They look like real people, but they are really just figments of the imagination of this model. And they're starting to look pretty realistic. So this is a fun example. I've seen real companies use that for designing new clothes, for coming up with new kinds of patterns for clothes, for new kinds of styles. So, we're starting to see some real applications of that in the industry as well.
Yeah, I don't know if you've seen, but there are these generated fashion models on Instagram where they're not real people, but they have thousands and thousands of followers, and people have created these fake human beings, and then they just put some influencer marketing behind it. Like they'll make a fake person and then show the person wearing Nike clothing and sell that to Nike, and they've got 60,000 Instagram followers, and it's just like not a real person, but people are purchasing advertising against this non-real human being. It's kind of I don't know, one of these things where it's like, wow, it really feels like you're living in the future when you have 60,000 Instagram followers to a artificial human being on a social network.
Yeah, those can get tricky as well.
Definitely. How has the TensorFlow model debugging experience advanced? Because you have people who train models and then they want to improve those models, and maybe they have some issue with the model that keeps coming up, like the model keeps tagging, whenever it sees a book, tags that book as a computer because it's also rectangular shaped, or you don't exactly know why it's tagging the books as computers. How does the debugging process advanced?
So there are a number of things that we've done in this direction, and let me talk about those one by one. So, one is the debugging from just as you're building a model, you want to understand maybe the model's not working and so on, and you want to, understand that better. And that's an area we think, with the whole idea of eager execution, where you're basically writing just Python code. What that enables you to do is to debug with Python tools. So any tool, any library you have in Python, or just your basic Python debugger, you can do whatever you want with it. You can set breakpoints, you can print out stuff, you can visualize stuff using standard Python libraries, and so on. So that's sort of one direction. Two, for a similar thing, sometimes you do want the graphs because they can be optimized much better. They can be deployed across the distributed cluster and so on really, really well. So let's say you have that. So for that, we have something called the TensorFlow debugger, which now, we recently announced this visual integration with TensorBoard as well. So you can actually, it's like your debugging environment that you might get in an IDE, and it looks really cool and it's great to debug. So those are from early programming debugging style things, right? Now, some of the other things you mentioned were around, understanding a model or understanding a specific mistake, let's say that the model made. And I think from a research perspective, there's been a lot of progress interpreting these models. So for a specific example, if it makes a decision or a classification, there are these tools that can help you really try and understand what parts of the inputs did they come from. So for example, for an image, and you mentioned a book gets classified as something else, you can see what part of that original image made the classifier, made that model think that that was the case. And then you can use some of this information. You can also look at different parts of your model itself. And you can use all that information to learn and think about ideas to improve that as well.
I was at the TensorFlow Dev Summit in 2017. I was unable to make it this year. At the 2017 event, there were presentations of applications for detecting skin cancer and diabetic retinopathy with machine learning models. But these applications were only being used in laboratory environments. And I saw these and I got excited because I was thinking, over the next year, we're going to be using our smartphone to scan something on our skin and detect if it's a freckle or if it's high risk and if we need to go into the doctor's office. But it's been a year and I haven't gotten a smartphone application that does that. And my sense is that that's because there is a barrier to getting these tools approved. What are the barriers to getting these kinds of low-hanging fruit medical applications of machine learning, these self-serve consumer applications? Why aren't we seeing more of these yet?
So I think from a medicine perspective, there are a number of things, right? There are the basic health kind of tools, and whether it's your Fitbit app or your Google Health app and so on, that thing that runs on your phone and tracks your progress, whether you're running enough or not, and things like that. Those can definitely have machine learning today and do the basics for you today. But beyond that, if you really want to build an application that really, complements your doctor or helps your doctor make decisions, you need to be much more rigorous and thorough about that. There's a good reason why medicine today, if you want to introduce a new medicine or a new technique, it needs to go through a process to get approved. And the reasons are, you don't want to get something out there which will make wrong decisions or which will lead doctors to make wrong decisions. You really want to be very, very careful in that. And so, that process takes a while. There are a number of applications like the one you mentioned for skin cancer and others that are starting to make their way through that process. And over time, I think we'll see more of these getting deployed across the board, not just in the US, but outside the US as well.
Something I saw from Jeff Dean's talk at the TensorFlow Dev Summit this year that was unbelievable to me was that the same images that were used to predict diabetic retinopathy, just these images of people's eyes, they could also be used to predict age and gender. So you have this labeled data set of eyes, just images of close-up eyes. And you think, okay, great, we've got a labeled data set of eyes. How useful can that be? Certainly you can detect diabetic retinopathy with it, but the fact that you can predict age and gender is remarkable. And I think there's been work around predicting risk of heart disease just from looking at eyes. Are there other instances you've seen where these data sets have produced, and I guess it's probably high fidelity, unstructured data that has a lot of detail that is hard to interpret to humans? That's probably the class of data set we're talking about. But have you seen any other unexpected predictions that have blown you away?
This one definitely beats everything else I've seen. I mean, you mentioned unstructured data set, and that's definitely true. Like in this case, most people had no idea you could do that. And as you saw in Jeff's talk, the folks who were doing this were also extremely surprised. This was more just a test and just, a process that we were trying to go through to help somebody learn about how this whole thing works. For other areas, I mean, I can see more of this happening as you find, these models are incredibly good at finding fairly complex patterns of things. So, as we provide different kinds of data, I expect to see more of this. But that said, no, I haven't seen anything as amazing as this.
I wonder what the other data sets that will be worth exploring for this kind of thing. Like, I can imagine pictures of planets, and maybe if you have some idea of the chemical composition of the atmosphere in those planets, maybe you can figure out more about the physics associated with those chemicals that are in those atmospheres or something like that. I'm trying to think of something that's analogous to these close-up images of eyeballs. Nothing's coming to mind, but I don't know, maybe you can let me know if you think of anything.
Yeah, one of the things that, the reason we could actually show that it seems to be related and that you could predict is that the data set had the values from the people as well. Like we knew the data set had the gender value and so on. So you could take that out for making the predictions or for learning and so on. You could learn from that and then make the prediction. For a lot of the things, like the example you said, the hard thing would be you need a data set which has those values first, where we have strong confidence because of other things and so on. But that said, yeah, it will be interesting to see. I honestly can't think of any crazy thing like this. But yeah, I'm sure we'll see some.
Well, this is what makes me really excited and optimistic about the Google Project Baseline. This is something I'd really like to do a show about. I don't know if there's anybody out there that is in the Google Baseline project, but I think this is like where 10,000 people are getting tracked for like 10 years at close fidelity. Pretty exciting. What are some other simple but powerful applications that we're going to eventually have by just combining machine learning and the smartphone?
The most simple things that we see, of course, are you have the phone with you. It has things like camera and audio, and you use them for interesting things. So I'll give you an example of something that's deployed today. So if you buy a Pixel 2, then the camera on that device, when you take a picture of a person and so on, in portrait mode, it basically separates the foreground from the background for you. And it basically it has this effect that's called the bokeh effect, which basically, fuzzes the background essentially and makes the person pop out really well. So this was all done using machine learning on the phone, using existing stuff on the device. I think the interesting thing on phones and other devices is also going to be what's the information that goes into there, right? So what's the information that this device is getting? In the case of phone, it has all kinds of sensors. The most common ones we think of are the audio, the speaker, and the vision sensor, the camera. And I think the combination of those is going to be very interesting in terms of what you do with that on the device itself.
All right. Last year, the focus was on usability for the TensorFlow team. What's the focus this year?
I think it doesn't let up. So I would say a couple of things. I think performance is where we started is a big thing. So performance and usability continue to be, important for us. I think last year we'd said we see TensorFlow as fast, it's flexible. So, we want to be able to do amazing things and production ready. So you can deploy these things into real world applications as well. So I think from the perspective of where we are, I think it's important for us to make sure that people can really use this in real world things. So we highlighted a number of things that were made with TensorFlow, and people are doing some interesting things. We would love to see more of that. We would like to see more integrations with all kinds of real world applications that people use. And I think we'll do lots of different things to really bring this to more people. And making it easy is just one. Another example is the JavaScript thing, which I think enables a new developer community or a different developer community necessarily, potentially from the Python community, which is excited about this and can do lots of interesting things.
Yeah, and we're going to do a show in the near future about TensorFlow.js, so we'll be doing a much deeper dive there. Rajat, I want to thank you for coming on the show. It's been great talking to you once again.
Thanks, Jeff. It's always a pleasure to be here.
We are running an experiment to find out if Software Engineering Daily listeners are above average engineers. At triplebyte.com/SEDaily, you can take a quiz to help us gather data. I took the quiz and it covered a wide range of topics: general programming ability, a little security, a little system design. It was a nice short test to measure how my practical engineering skills have changed since I started this podcast. I will admit that, though I've gotten better at talking about software engineering, I have definitely gotten worse at actually writing code and doing software engineering myself. But if you want to take that quiz yourself, you can help us gather data and take that quiz at triplebyte.com/SEDaily. We have been running this experiment for a few weeks, and I'm happy to report that Software Engineering Daily listeners are absolutely crushing it so far. TripleByte has told me that everyone who has taken the test, on average, is 3 times more likely to be in their top bracket of quiz scores. And if you're looking for a job, TripleByte is a great place to start your search. It fast-tracks you at hundreds of top tech companies. TripleByte takes engineers seriously and does not waste their time, which is what I try to do with Software Engineering Daily myself. And I recommend checking out triplebyte.com/SEDaily. That's triplebyte.com/SEDaily, TripleByte, byte as in 8 bits. Thanks to TripleByte for being a sponsor of Software Engineering Daily. We appreciate it.
Wow.